All right, in this video, I want to start by talking about number systems and bases and what it means to write a number with digits on a whiteboard. So we learned this at some point in fourth grade and then kind of stopped thinking about it. But when we write a number that has multiple digits, those different digits are in different places, right? We say like the ones place or the hundreds place. And that is ascribing a value to that digit. So for example, when we write the number 23, what does this mean, right? Well, we know that if we think way back, this is the tens place, this is the ones place. And so what we're really saying here is this is 2 times 10 plus 3 times 1. So the 2 is worth 10 for each of its 2, and the 3s are only worth 1. So anyway, you combine those and you get this 23 value that we know about. So what's actually going on here is a specific case of a bigger framework that is what we call the base of the number system. So this is, what we normally use for writing numbers is base 10. And that means that these places, and of course the, hundreds place, thousands place, 10,000s place, etc., the value of these increases by a factor of 10 each time. So really, when we have these digits that we'll call D for digits. So we have like D0, D1, D2, D3. Whatever number we have for these is each of these digits multiplied by the value of each of these places. So we have something that looks like, and we'll do it right to left here since that's the lowest value, right? We have something that's like D0 times 10 to the 0 plus D1 times 10 to the 1 plus D2 times 10 to the 2, and so on, right? We can build our number bigger and bigger to the left. So the ones place is 10 to the 0, the tens place, the hundreds place, the thousands place, and so on. So the 10 here is called the base, right? So our number system is in base 10, and there's nothing particularly special about 10 for this. There is really only 10 things special about 10 that make us use a base 10 number system. We could use any number here, and there are a couple common other ones that are worth knowing about. So base 2, also known as binary, is a way of keeping track of numbers where the number places each increase by a factor of 2, right? So instead of the ones place, the tens place, the hundreds place, you have the ones place, the twos place, the fours place, the eights place, because it is, it's D0 times 2 to the 0 plus D1 times 2 to the 1 plus D2 times 2 to the 2 plus D3 times 2 to the 3, right? So this is 1, 2, 4, 8, etc. So this is how you write a number in binary. It turns out for any decimal system like this, I shouldn't say decimal because that means 10. For any number system like this, the number of digits you need is equal to the number of the base. So for our base 10 system, we have 10 different digits, different symbols that we can use to write the values in each of these places, right? 1 through 9 and 0, right? It can also be, we could have a 0 in the ones place too. That's perfectly fine. In binary, we only need 2 values, and so that is 0 and 1. So all of our digits are either 0 or 1, which is really the whole point of this, because now our on-off Boolean variables in the computer, or our flip-flops or our latches or whatever, can be storing this piece of information, and connect to other things storing that same piece of information. So these digits in the binary system are called bits, which is literally short for binary digits and kind of also a cute name for these little bite-sized pieces of information. So in the last video, we had the 3-bit counter. So that meant that we could write a number with 3 binary digits, right? We had a 1's place, a 2's place, and a 4's place. So the biggest number we could add up would be 111, which is 1 plus 2 plus 4, which is 7. And if we try to add one more, as we saw with the flip-flops, the counter went back to 0. So there are 8 different numbers we could count with these three bits. If we added another bit to our counter, another flip-flop to our counter, that would have given us another bit, another piece of information. And instead of 2 to the 3 states, we would have had 2 to the 4 states. And so we could have counted up to 15. That is, 16 minus 1. All right. So let's erase this. Yeah, this is good. One other base system that's worth talking about is hexadecimal. Hexadecimal turns out to also be very useful for computers and digital electronics. So that is base 16, where now instead of just 10 symbols, we actually need 16 symbols. So it uses the letters A, B, C, D, E, F, in addition to numbers 0 through 9 to represent the digits of a number. It turns out because 16 is a power of 2, it is very, very easy to translate between hexadecimal and binary. And so lots of computer stuff is done in hexadecimal. Maybe we'll do a little bit of that later on the Arduinos, but we don't need to talk about that right now. Okay, so what if we have a number in binary? Like, how do we figure out what that is? So let's say we have a number that looks like this, 1101. And for clarity, when we're writing a number in binary on the board, to make it clear that it is binary, I'll put a little subscript 2 here to show that this is base 2. Right, so if I wrote 1101 with a little 10 down there in base 10, this is 1101, right? So this is like, 101 more than 1,000. This is like a big, a big number. In base 2, those same digits in the same order is not a big number, right? So this is the 1's place, this is the 2's place, this is the 4's place, this is the 8's place. So this number is equal to 8 plus 4 plus 1, which is equal to 13. So, so that's why this subscript is important, especially especially if the numbers are only 1s and 0s, it can be ambiguous for what we're talking about. So that's how we can get from binary digits to a decimal number that we recognize. And I should put a 10 there if I'm being extra careful, even though the 3 was a giveaway. We know it's not binary, but that's a good, putting the subscript there is a good practice. Okay, lastly, I want to talk about how we count up in binary. So counting up in binary is the same as counting up in decimal, meaning when we run out of values to put in a place, we carry a 1 to the next place. The only difference in binary is we have to do that a lot because everything is only a 0 or a 1. So here's how we count in binary. We'll do our I'm gonna write the leading zeros just to remind us. But we don't have to do that. So we add 1 to this, we get 0, 0, 0, 1. We get the number 1. If we add 1 to this, we can't have 2 here, so we have to carry a 1 to the next place. I can add 1 to that, though. If I add 1 to this, that can't be 2, so I have to carry a 1 to here. But that can't be 2, so I have to carry a 1 to here. So we get 0, 1, 0, 0. 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. You can probably see the pattern. So in terms of our base 10 numbers, this is 0, 1, 2, 3, 4, 5, 6, 7. And now if we add 1 to this, that can't be 2, that can't be 2, that can't be 2. So we carry the 1 all the way to the left, and everything else is a 0. And this is 8, which makes sense because this is a 1 in the 8's place and 0s everywhere else. I'll just do a few more. I'm not going to go all the way to 16, but so it's this, the rest of it literally is just the same as this, but with a 1 in front. So we have 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, etc. So this is 9, 10, 11, 12. All right, so that is how you count up in binary. If you look at the last video and how the flip-flops were changing, you'll see that what we saw was exactly these digits, where this column was Q0, this column was Q1, and this column was Q2. So these different digits, the different values of these bits, of these digits, has to do with which of the 3 flip-flops we were looking at. So in if we're talking about which ones are which, sometimes you can represent them 0, 1, 2. Sometimes that might be ambiguous, but it's always clear to refer to this digit as the least significant. The least significant digit or the least significant bit. And in the case of this 3-bit counter, this third one is the most significant bit. In the case of this bigger 4-digit thing we've done, this fourth one would be the most significant bit. This can be important because different systems can, I wrote bit, but it could also be digit just to keep it consistent with the other one. So, yeah.